today's lecture I will be talking about the lattice vibrations. Lattice vibration is an aspect of solid state physics, and for today's lecture I will be using the books Introduction to Solid State Physics by Charles Kittle, Solid State Physics by M.A. Wahab, Solid State Physics by R.L. Singhal, Solid State Physics by Ashraft and Mermin. I will also refer to a few more like Decker, Solid State Physics by Decker. So, what is a lattice? In solid state physics, we start with a lattice. We assume a lattice is a regular arrangement in any crystal. A lattice is described as a regular arrangement of points, and to each of these points when we attach a basis which is either a single atom or a group of atoms, that will constitute the entire crystal structure. Today's lecture I will be talking about the lattice vibrations. This is the lattice, and we have a regular arrangement of atoms or a group atoms at regular intervals. The entire lattice can be regarded as an array of atoms which are connected by ideal elastic springs. Ideal elastic springs are also called the ideal Hooke's law springs. These springs, that means they obey the Hooke's law. Hooke's law is if there is a displacement, then the restoring force is proportional to the displacement, and this is valid within the elastic limit. The motion of every atom in this case would be shared by all the atoms in the crystal, and if there is any vibration in one of the lattice points or one of the atoms, the crystal would vibrate as a whole. We start with so when I am talking about the vibration of a crystal, we will talk of two different aspects. First one, today I will be talking about the elastic vibrations of a one-dimensional line. Let us consider this yellow one, the one-dimensional line of length, homogeneous isotropic elastic line of length x, which is extending from x to x plus delta x along the x axis. Now, I am talking of homogeneous isotropic lines. That means the properties of the material is same all throughout. Also, the properties are same in all the direction. This is what I mean by homogeneous and elastic lines, okay, and isotropic lines. Now, this is extending from x equal to x plus delta x. That means there is this line is of length delta x. Now, in presence of a stress, an elastic strain will be produced. At equilibrium position, the left end of the element, let it be displaced by an amount let it be displaced by a distance u along the x axis, and let the right end be displaced by an amount u plus delta u. So, the forces on both the ends of the line is not the same. On the left end the displacement is u, on the right end the displacement is u plus delta u. Therefore, the elastic strain, which is defined as the elastic extension of the element per unit length, will be given by Sx, which is limit delta x tending to 0, delta u by delta x, which is equal to del u by del x. Now, we are dealing with a one-dimensional structure. So, the usual definition of stress, which is force per unit area, cannot be used. Hence, here we have to deal with the force itself. Let C be the longitudinal stiffness of the material, and then the force will be C into S, and C longitudinal stiffness is related to Young's modulus C11 by the relation C11 equal to C by A square. In this case, A is the spacing between the one-dimensional lines if they are assumed to compose the three-dimensional solid. That means I am assuming that my 3-dimensional solid is composed of these 1-dimensional lines which have a spacing of a between them. Then the force at point x will be C into Sx. The force at point x plus delta x will be C into S plus delta x. This I can write it as C into Sx plus del S by del x into delta x. This I have attained by using a Taylor series expansion of Sx plus delta x, and I have neglected the second order and higher order terms. Second order and the higher order terms are neglected, only the first order term is taken. So, Fx plus delta x will be given by C Sx plus del S by del x into delta x. The forces at the two ends of the element, they are opposite to each other. So, the resultant force will be a difference between these two forces. So, Fx x plus delta x minus Fx will be equal to C del S by del x into delta x. Now, this force must be related to acceleration of the element by Newton's second law. Newton's second law is force equal to mass into acceleration. In this case, the force is C del S by del x into delta x, which is equal to mass into acceleration. And what is acceleration? Del square displacement by del t square. In this case, the displacement is u, so it will be m d square u del square u by del t square. Now, if the density of the rod is rho, that means rho will be the mass per unit length. So, the mass of the rod can be written as rho into delta x. Acceleration is del square u by del t square. With these values of m, if I and from the values of Sx from my equation number 1, then I can write C del by del x into of del u by del x into delta x will be equal to rho delta x into del square u by del t square. This, after rearranging, can be written as del square u by del x square equal to rho by C del square u by del t square, which also I can write it as 1 by Vs square del square u by del t square. In this case, rho by C is 1 by Vs square. This is the wave equation for the amplitude of the elastic waves in the line where the elastic strain is confined along the x-axis. This is the wave equation for the amplitude of elastic waves in the line where the elastic strain is confined along the x-axis. And this solution 3, it represents a sinusoidal disturbance of frequency omega, which is equal to 2 pi nu, and wavelength is 2 pi by k. This is propagated along the, and the wave is propagated along the x-axis. If I substitute equation 3 back in equation number 2, then we will find that equation 3 will be satisfied only when omega equal to k into under root of c by rho. This is called the dispersion relation for an elastic for a homogeneous isotropic line, and this relates dispersion relation, it relates the frequency with wavelength. The variation of omega with k will be given by this form, that means it will be a straight line, and k is the wave vector or the propagation vector. K will be the wave vector or the propagation vector. K vector, the propagation vector, it points in the direction of the wave normal and it represents a mode of vibration. K represents each value of k gives me a different mode of vibration. We know that phase velocity is given by omega by k. The group velocity is given by d omega by dk, and because omega by k and d omega by dk. Omega in this case is k under root of c by rho. So, what will be Vp, which is omega by k, that will be under root of c by rho. Similarly, Vg, which is d omega by dk, will also be under root of c by rho. That means which is equal to Vs. In both these Vp and Vg will be independent of frequency and wavelength, and the same result, this is the same case for sound waves. This means that the wave that is propagating the elastic vibration of a continuous homogeneous line, they are same as that of the sound waves, which means that the wave that is propagating through the homogeneous isotropic line is a sound wave. A sound wave is propagating through the homogeneous isotropic line. Coming to the normal modes of vibration in a finite length of the line. Now, normal modes are regarded as the independent solutions of the wave equation 2, which satisfy a given set of boundary conditions. So, let us assume the boundary condition in this case is that the two ends of the line are rigidly fixed. That means they cannot have any displacement at all. Under this condition, a standing wave will be set up in the line, and the solution of this u equal to u naught e to the power of I omega t minus kx, the solution will be u naught sin of kx into sin of omega t. Now, if we look at this equation number 6, sin of omega t cannot be equal to 0, then u will be 0 for all time. U naught also cannot be equal to 0, that means the amplitude of the wave is 0, which means u will be 0 for all time. So, the only quantity which can be 0 is sin of kx. Now, sin of kx can be 0 only when at the end at x equal to 0 and at x equal to L, it is this quantity sin of kx which should be equal to 0 for u to be 0 at x equal to 0 and at x equal to L, and these two quantities can be 0 only when sin of kx can be 0 only when k is n pi by L. That means k can have values pi by L, 2 pi by L, 3 pi by L and so on up to n pi by L. N can be any positive integer. In this case, what we find is k equal to 0 is to be excluded, because if k becomes equal to 0, that k equal to 0 implies n equal to 0. N can only have positive integral values. K equal to 0 is to be excluded since this corresponds to all the particles at rest. So, the frequency spectrum in this case k equal to 0 is excluded. Now, look at this k, the values of k. What the most interesting part is k cannot have a continuous values. K will have only discrete set of values, that is pi by L, 2 pi by L, 3 pi by L and so on up to n pi by L. That means my frequency spectrum in this case is discrete. Let us see what will be the shape of the wave when n equal to 1, that will be the two edges are fixed and we will have the two antinodes, nodes at the two ends. The antinode will be in the center. When n becomes equal to 2, we will have 2 loops and so on, is for the independent line of atoms. So, for a homogeneous line of atom, elastic vibrations This means that the elastic vibrations in a homogeneous line of atom will be sound waves. The wave that is propagating through a one-dimensional line will be sound waves only. They can have, and the second most interesting fact is that these waves, they will be the wave vector of these waves will be quantized. These waves cannot have any values of k, rather they will have only certain values of k equal to pi by l, 2 pi by l, 3 pi by l and up to n pi by l. My dispersion relation in this case is totally independent of both frequency and wavelength. This is the case if that means the wave that is propagating through the system is a sound wave. It is independent of frequency and wavelength. Elastic vibrations are sound waves that are propagating through the material. And what is the phase velocity and group velocity are the same, that is equal to under root of c by rho. So, what have we learned today? What is a lattice? The lattice, I can take it as a simple, I can take my lattice. Lattice, we have the periodic arrangement of points in the lattice, and those that I can consider as being connected to each other by ideal Hooke's law spring. So, any vibration that is produced in any one of the lattice points will be transmitted to the entire lattice by the lattice by these ideal Hooke's law spring. These are not real springs that are there. These are the springs that we presume is there within the lattice, because what we find is any disturbance or any dispersion that is produced in the lattice, any force that is applied at one end is getting propagated through the entire lattice, and the wave that is propagated in the lattice are the sound waves. These sound waves are quantized and they can have values of having k between pi by l, 2 pi by l, 3 pi by l and so on and so forth. Okay. This is all for the elastic vibrations of a line of atoms. In the next lecture, we will be talking about the monoatomic chain of atoms. That's all for today. Thank you.